Okay, everyone, now we're at the hardest part of Chapter 7, which is how do we tell what reaction it's going to be? We've learned SN1, SN2. We know that there's competition between those, and now we're throwing into the mix E1 and E2 as well. And what happens is sometimes you get multiple reaction pathways happening at the same time, but we're interested in the major pathway, trying to find that, and oftentimes some of these occur together. So let's take a look at how we know for a given reaction which one of these four is going to be lead to the major product, okay? So first, it's important to distinguish between basicity and nucleophilicity. Now remember, nucleophilic substitution, really depends on the nucleophilic strength, whereas E1 and E2 elimination really depends on basicity and base strength. So let's look at hydroxide. We know that's a strong base. So a strong base is going to grab a hydrogen and it's going to be product favored for these ions and molecules. Now a nucleophile like hydroxide or methoxide, a nucleophile is related to kinetics. You know, how likely is this to come in and displace this group in a substitution reaction? This is pretty small, so it's going to be not asterically hindered. So it's going to come in and it can, instead of taking a hydrogen, it can attack the R group and do substitution. In an example of a hindered base, so bulky base like tert-butoxide, it's going to be less likely to come in and attack the R. It's probably more likely to grab a hydrogen out here. So a bulky base is going to favor elimination, not so much substitution. So here, this is more reactant favored than product favored. And then here we have a weak base, whereas these guys were strong bases. This was a good nucleophile and this was not so good because it's bulky. Here we have a weak base, but even though it's a weak base, it's actually a good nucleophile because it's polarizable. So let's look at how do we know from looking at something, whether it's a good nucleophile or a poor nucleophile or a strong base or a weak base. It can play multiple roles as well. So hydroxide, methoxide, ethoxide, any kind of non-bulky R group. It's going to be a good nucleophile because of the base strength of the O, and it's also good at attacking carbons. And it's a strong base as well because it's really great at getting hydrogens also. So think of these as strong bases, good nucleophiles. Then we have good nucleophiles, but they're weak bases. They're good nucleophiles though because they're polarizable. Now strong bases can be bulky, and that makes them not so good at attacking carbon. So these are poor nucleophiles. And you might be familiar with tert-butoxide. We've been using that a lot. But DBU and DBN are also molecules you might see in the textbook that are used for practice problems. They're pretty bulky as well. And then over here, these are poor nucleophiles and weak bases. And notice the pattern here. They're neutral alcohols and water have the similar pKa, 15, 16. So it's good to remember these in a group. So if you see an alcohol or something neutral, you know it's going to be a weak base or a poor nucleophile. So in thinking about the four pathways, we know good nucleophiles favor SN2 and poor nucleophiles favor SN1 because the leaving group leaves first. We also know strong bases favor E2 and weak bases favor E1. So a lot of times just looking at that is going to be sufficient. But you also want to look at the starting material, if it's primary, secondary, tertiary. Remember, E1 and SN1 go through carbocation intermediates. And we know that E2 happens quickly and in an anti-periplanar fashion. So you want to eventually know this. I wouldn't say you want to memorize it, but you want to look for patterns. Like if I see oxygen negatively charged with a pretty small R group, it's going to be a strong base and a good nucleophile. Like I just know hydroxide, and these are analogs. Here, this is water, so these are all neutral versions of these. These are the conjugate acids of those, and they're neutral. So I know that's going to make them a lot weaker as a base. So use concepts like that. Here, this is charged, so it's a good nucleophile, but it's also larger than oxygen. That makes it more polarizable. So remember those two concepts of charge and polarizability. That's what's going to lean you towards the good nucleophiles. So without looking at your chart, if possible, see if you can identify first is this a good or poor nucleophile, and is it a strong or weak base? And maybe make a chart like nucleophile versus base. We know this one is neutral, so that's going to be a poor nucleophile. And then it's also a weak base because it's like water. It's OH2 or ROH. This is an alcohol, so it's a weak base. Okay, so do your best to go through without looking at the chart, and then look at your chart to check your answers. All right, guys, we're back. So if you take a look, this is neutral, but it's larger and more polarizable than oxygen. So this is actually a good nucleophile, but it's neutral, so it's a weak base. This is a good nucleophile because it's like hydroxide, but with an R group. So it's good, strong base, good nucleophile. This one's a good nucleophile because it's polarizable, but it's a weak base. Its conjugate acid, HBr, is very strong. Now for these guys, you have to be careful. If you see lithium or sodium or potassium, these are actually salts. So you want to do the dissociation and look at the conjugate. You want to look at the base here. So this is a hydroxide, but this is methanol. So be very careful here. This, you do not dissociate the methanol, the methyl group. So here, though, this is sodium ion, and so you have methoxide left over, and that's a strong base, just like hydroxide is. Look at the similarity. So, and if you're not sure, you can just go back here and sort of look and check it out. Now, with substitution and elimination, some major differences here. SN1 versus SN2 has to do with the carbocation. You can look at, SN1 prefers tertiary, and SN2 prefers methyl and primary. For E1 versus E2, it's not so much the substrate structure, but it is for E1 because we definitely need a carbocation in that case. And E2, you could have any substituted, either you can't have a methyl because there's no beta hydrogens, but you could have primary, secondary, or tertiary for E2. Now they all start to compete with each other. And remember when we were looking at SN1 versus SN2, remember the secondary alkyl halides? They could go either way because secondary wasn't terrible as a carbocation, and it also wasn't terrible for steric hindrance. So you had either option there. So now we want to see how these all compete with each other. First, let's take an example here, SN2 versus E2. Okay, so we know there's no carbocation intermediate. We have a good base and a strong nucleophile. So let's say that in that situation, for primary, that really favors substitution just slightly because you know that the smaller the base, the less crowding, and primary, the less steric crowding there is. So that means nucleophilic substitution is going to be a little bit favored. And then for secondary, it's sort of, both of them can happen almost equally. The gap starts to close here. But by the time you get to tertiary, actually E2 is way more favored than SN2. So let's take a look at why that is. So in the E2 pathway right here, let's say we take this tertiary. I've got a strong base. Even though it's small, it's still going to prefer to grab right here. All right, so I'm going to get my Zaitsev product in that case. Now for SN2, even with a small base, it's still not small enough. It's going to be sterically hindered here. These methyl groups are going to provide electron repulsion. So it's going to be very difficult. We're going to say basically no reaction there. So that's why this plummets right here. Now with E2, E2 loves tertiary because this alkene is more substituted, and that's lower energy than if I had a primary and I had less substituted alkenes. So that's why E2 is favored so much more there. So for our purposes, let's say that if you have primary, let's count both SN2 and E2. And then if we have secondary, we get both as well. But if we have tertiary, definitely do not give me any SN2 product, only E2 product, given the conditions that allow that. The next thing I want to show you is about the reagents. We definitely want to consider good versus poor nucleophile and strong versus weak base. And good nucleophile, I think it all goes back to what I wrote up here. Good nucleophile SN2, strong base E2. Weak base, poor nucleophile, SN1 and E1, And I want you to notice that they both sort of tend to happen together. These two tend to happen together because you're going through a carbocation, and usually that means you can have elimination and substitution with that carbocation. Temperature-wise, I think if you recall, elimination produces a lot more products. I think you get 3 products instead of 2. So notice with elimination here, you're taking these 2 molecules and you're making an alkene, but you're also getting water and you're getting bromide. So you're getting 3 things. So entropy increases quite a bit. Whereas with substitution, you start with 2 things and you end with 2 things. So since the entropy factor is so much higher, when you think back to this equation, as this becomes a more significant factor, then temperature also can affect that. So what we tend to see is that reactions drive toward elimination when you increase these 2 factors. So especially temperature. Temperature drives the delta G to be more negative for E2 and E1. So for temperature, increasing the temperature makes delta G more spontaneous. So for elimination especially, because the entropy factor starts to play a role, E1 and E2 favor heat. So I'm going to put a heat symbol, or sort of make a note that 50 degrees, 100 degrees C, these are considered heat. And then keeping it cool, this substitution. So we're going to keep it cool, room temperature 25 degrees C or 0 degrees C. That keeps things from eliminating. So that's one thing you might look at when you see a reaction. And then also stereochemistry, I want you to keep track of both stereochem and regiochem. What that means is, remember, for SN2, we have inversion. So if something is chiral with a center that is R, then the product is likely to be S. We have SN1 is racemic mixture, if it's chiral. If we have elimination, we have Zaitsev regioselectivity here. We have E2 with a strong base can be Zaitsev versus Hoffman, depending on how bulky your base is. And then we also have anti-periplanar for E2. So these are all things that affect what stereoisomer or what constitutional isomer you're going to get. Okay, finally then, how we put it all together is to have our choices up here. We have SN1, SN2, E1, and E2. And for these, I want you to find out what is your major pathway and what is the product. And it could be multiple. It could be, like I said, E1 and SN1 tend to happen together because you have a weak base, which is also a weak nucleophile. So I want you to think of all the different pathways that could be possible and write your major product or products. So let's do a few of these together so you get used to it. And then I also have a bunch of practice worksheets in the workbook. So we've got, first, I like to read these left to right. So here I have a secondary leaving group. And so secondary means everything's possible. So now I look at this part and I have chloride. And chloride is a good nucleophile and it's also a weak base. So think about what all the possible reactions are in this scenario. So good nucleophile means SN1 or SN2. Good nucleophile means SN2, and a weak base means E1 or E1, right? Because base has to do with elimination. Now the thing is, if I have a choice between having a nucleophile come in versus waiting for the leaving group to leave as an E1 and then having this grab a beta hydrogen, it's more likely that this is just going to come in. I'm not going to wait for this leaving group to leave first. So this as a nucleophile is going to come in, and I'm going to choose SN2 over E1 because I think E1 and SN1 are pretty slow. You know, they have to wait for the leaving group first. So what I'll do is, if I have a choice, I'm going to pick SN2 or E2 over SN1 and E1 if they're also possible. And I'm going to show this coming in from the back and displacing that. This is an SN2 product. And then I want to show what that SN2 product is. Now this is a chiral center, so I want to make sure that my stereochemistry is correct here. So the last thing I'll say about this one is DMSO promotes a faster SN2 reaction because this is aprotic. Now I would say that the solvent has a really profound effect on the rate, but sometimes it can change the reaction pathway, but usually you don't see that, and sometimes you don't even see a solvent specified. So I'd say of all three factors, definitely what substitution it is and strength of the nucleophile base is more important, but sometimes you see the solvent as a clue as well, so aprotic. So let's try part B now. And so again, we're reading from left to right. So I want to look at the structure of the substrate. This is tertiary leaving group. So that means I can't do SN2 like I did here. It's too bulky here. I can do SN1 and E1 because they make a carbocation. But I can also do E2 because I can grab beta hydrogens. There's lots to choose from. So now I have to look at this to figure it out. This is a strong base and a good nucleophile. So that means it's going to come in and grab an H before I can even wait for the leaving group for SN1 and E1. So this is, even though all three of these, SN1, E1, and E2 are all possible with the tertiary, this strong base is going to drive it to E2. So whenever you see strong base, I want you to think E2 most likely, and then maybe some SN2 sometimes. So first step is this is going to dissociate, and then first step is I'm going to have a beta hydrogen come in, base comes in, grabs that, and I have this kind of reaction here. So with a small base like hydroxide, I want to make my Zaitsev product. So notice what I'm doing here. I'm making sure I'm thinking about stereochemistry. I'm thinking about regioselectivity, Zaitsev versus Hoffman. And I'm also writing down which pathway. SN2, this product. E2, this product. And to myself, I'm sort of rationalizing it. Why did I pick E2? Why did I pick SN2? Or why did I eliminate the other choices? So think about that as you go through these. And let's check our answers with each other in a few minutes. Okay guys, so this is what I have so far. Looking at this bulky base, but it's very strong. So strong base, I want to think about elimination. So E2. And I have beta hydrogens out here, and I have this one in here that's going to be surrounded. So more electron repulsion to grab this one. So I get my Hoffman. And same for DBU, being a strong, bulky base, it's going to grab a terminal hydrogen, but now I have a benzene ring, so it's a benzylic position, which helps to stabilize that. Here, this is also a strong, bulky base again, so looking for our places here. You might get a little bit of substitution here, but again, this is very bulky, so you definitely get less of that. So I would say E2 is our major product here. We have this sulfide ion come in and just do displacement SN2. This is a good nucleophile, so that's why SN2. Not really E2 because it's not a strong base, it's a weak base. For G, we have hydroxide, which is a good nucleophile, strong base. So good nucleophile means it's going to do SN2. Strong base means it's going to grab beta hydrogens and do E2. All right, so up here I've got ethoxide, which is a small, strong base. So E2 for strong base and small. Actually, there's only one beta hydrogen. So I wouldn't call it a Zaitsev or Hoffman product because you only have one choice. So this is just this alkene. Then with E2 Zaitsev product here, oh yeah, what I'm getting is E1 because this is a weak base. It could do E1 or SN1 with ethanol. But with heat, that's going to drive it toward E1. So this is going to leave, and then I'm going to get a positive charge, no rearrangement, and a Zaitsev product. Here, a small, strong base, E2, leading to Zaitsev rather than Hoffman here. So, and then notice that this can rotate. So I'm going to get probably a combination of the cis and the trans. The trans is going to be a little more stable. So I'll put just a little bit of cis as well, but my major is going to be trans because it's more stable. Same with methoxide. It's going to be basically just like with hydroxide. So I'm going to get a little bit of cis as well here. And then with this one though, notice that all of a sudden we don't have our choice of hydrogens. So I'm assuming to take whichever one is antiperiplanar to bromine at any given time. But what's going on here is I've got one of those hydrogens replaced by a methyl. So I can only take the bromine when it's antiperiplanar to this hydrogen. So I'm going to rotate this bond until bromine's in the front, which is the opposite side as my H. And then you'll notice that this methyl got moved as this bromine came up. So methyl's pointing up now instead of pointing down. So this is going to give me my E or trans isomer only. And then, whereas before I had cis and trans, a mixture. And then here for E2, I'm going to have a small base, strong base come in, and again, antiperiplanar. This hydrogen that's beta is same side as the leaving group, so I'm not going to grab this hydrogen, I'm going to grab this one. So that's why I get this product here. And if I switch the methyl group, so now the hydrogen here is in the back, now these are antiperiplanar, so I'm going to grab this hydrogen and make the more stable alkene in this case. So both of these have to do with antiperiplanar geometry. Now something that I got from Andre Stromanis' book is this nice little flow chart here. It's a decision tree. And you can see that the first thing is just knowing, is it a methyl leaving group, primary, secondary, or tertiary? And then from there, good nucleophile or poor nucleophile would be your next question. Strong base or weak base is also your next question. And then you have temperature that sort of can steer you one way over the other. So you might want to refer to this maybe just as you start off, but you want to get to the point where you don't need to rely on a chart, because that you really want to rely on your concept knowledge. Now, I always ask some of these critical thinking questions because I want you to know the reason behind why which pathways favored and why. So, why is it that polar protic solvents favor SN1 over and E1 over SN2 and E2? Why is it that, tertiary leaving groups don't work well in an SN2 reaction? So I want you to be able to look these over and sort of see if you can reason out those concepts. And then finally, I've got lots more practice where you have the substrate, a nucleophile or base, and the temperature. Sometimes you have a solvent. So I got a lot of questions about things like this. Let me just point out B here. It's a little bit tricky. I have an allylic leaving group. This is primary allylic. Remember, allylic means through resonance stabilization, carbocations are okay, and also nucleophiles are okay to come in because the pi system's over here, so it's not going to be too sterically hindered to attack here. So I've got a good nucleophile, but it's also a strong base. So I've got two options for this. I've got SN2 because it's a good nucleophile, but E2 because it's a strong base. So it's fine with me if you put both, but I do want to note that with the elimination, what's going to happen is you're going to only have this one beta hydrogen, and it's sp2 already. So that makes for an awkward situation where you have two double bonds like this. So what this is what we call a cumulene, and it's two double bonds. It's actually pretty reactive, so that's sort of a high activation energy. So I'm going to say that we're not going to form cumulenes in these cases, so let's go ahead and just do SN2. And then the next question I get is about the solvent. Notice that the solvent is protic. Now, sometimes they might say, that this nucleophile is in high concentration, so that means that the solvent is less of an issue. If this was low concentration, then basically we have mostly protic solvent, which then would probably lead you to thinking SN1 rather than SN2. So for us, let's go ahead and assume that these nucleophiles are in high enough concentration that they're going to lean toward SN2. But the solvent, the reason why this is a protic solvent rather than an aprotic is that the conjugate acid of my nucleophile, OCH3-, that's the conjugate acid. So that means when this molecule or this ion sees this one, So that means whenever I have my methoxide encounter, well, first of all, it's stabilized by this, which is not so great for SN2 because I want this to be potent. I want it to attack here. So protic isn't my first choice, but it's very common to pair these because basically what happens is this ion will see the solvent and just deprotonate it, and what do I get? I get more of this again. So it's very common to see pairings like that. But what I would do is just assume this is in high enough concentration that my good nucleophile does attack here quicker than this dissociates. So I would still treat it as SN2, but just say it would have been a faster SN2 if I used an aprotic solvent like acetone or DMF or DMSO. And then a couple of students this week noticed an error in the answer key to Substitution and Elimination Worksheet 2. So I just want to point out for Part B that the more favored product is actually the double bond here instead of where I have it, because it's going to be more stable. And then over here I should have had inversion, so this should be a dotted line there. Okay, we'll do that now so you don't know the answers when you get to doing it later, okay? All right, so for practice, I'd like you to work through Substitution Elimination Worksheets 1 and 2.